Okay, so hello everybody. Thank you for a kind introduction. My name is Sanna Janker and I'm a technical application scientist from BioLegend. And I would like to thank you the opportunity to be here today and give this presentation. So the title is a full spectrum panel design, new BioLegend dyes and experimental consideration. So we are discussing about full spectrum specifically because most of our new dyes are designed for full spectrum instruments. So that's the reason. And myself, I'm originally from Finland, if you're wondering my accent, and I'm located in Houston, Texas right now. So outline of today's talk. First, I'm gonna give you the overview of multicolor panel design, mainly like things to consider regarding biology, your instruments, and the different fluors that you're gonna use. Then we will touch a little bit of different fluor families and the factors that are influencing the panel design and performance of your panels. And then lastly, we will close today's talk with some helpful web tools for panel design and then some things to consider. So this said, first we're gonna discuss about multicolor panel design. So things that you need to consider are the biology of your experiment, the instrument you're gonna use, and then which kind of fluors you will have. So firstly, about the biology. So when you start a new experiment, you of course need to know what is the experimental question that you wanna address, and then how you can answer to this question. So you need to define your parameters and then select the targets that you're gonna use to answer your questions. And then after that, you can define your gating strategy, which is really important when you are doing flow experiments. And then of course you need to know your instrument. So whether you have a conventional one or a full spectrum. So if you have a conventional instrument, you need to know which kind of lasers you have and which kind of filters you have. So you know what you can detect. And then if you have a full spectrum instrument, you need to know how many lasers you basically have in that instrument. And then of course you need to know the fluors that you are using. So there is different fluor families and different fluors, they have different brightness. And that, of course, affects on how you're gonna pair your fluors with the targets. So now we're gonna discuss a little bit more about these three different subtitles. So firstly, about the biology. So you may know that at BioLegend, we are helping our customers to build tape panels. And usually when the customers come to us, we first ask several questions like, what is your model that you are using, whether it's a human, whether it's a mouse, or is the non-human primate, and what is the outcome you are assessing and which kind of cells you are using. So that's also important because the cells are different and that affects how we are reading them. And also which markers probably are expressed that or could be expressed or are co-expressed. Because as you know, the different cells are expressing different targets and some targets are co-expressed and some not. And that then affects how you're gonna choose your fluors for these different targets. And then you need to have proper controls. So you need to have a single color controls and non-stained controls, of course. And that's the same thing for conventional and the full spectrum instrument. And then also, if some other things that you need to consider. So where is your targets located, whether they are like cell surface or whether they are inside the cell or intranuclei, because that will then affect on the special buffers or fixation or permeabilization you may need to use. And some of the fluors are not that resilient what comes to the fixation and permeabilization. So you need to know these aspects also when you plan your experiments. And of course, whether your cells are having strong autofluorescence, how you're gonna prepare your samples, and etc. So once you know your targets and you know more or less what you are looking at, you can start to draw your gating strategy. So this is really important and it helps you analyze your downstream analysis, and it also helps you to create your multicolor panel. Because here you can see like which targets you are straight comparing with each other and what you are actually looking at. And then this will help you to design your panel. So you can draw your gating strategy with your computer when it's a really clean and nice, but you can also use just your notebook and pen and just draw it there, which is usually easier and faster and most convenient way. Or you can also create this kind of hierarchy, a tree, where you have first your starting material, like a human blood cells, and then you go further to divide them in subgroups like monocytes, lymphocytes, and then further there on, and then mark here which all markers these specific cells are expressing, and create your gating strategy based on that. Also, if you are not sure which kind of markers your cells are expressing, there is a lot of information, of course, online, the publications, and also on BioLegend website. So you can go biolegend.com/essential markers, where we have, for instance, for human and mouse, we have listed the different cell types and then the few essential markers that are expressed on these specific cell types. So this will help you to get started at least. And then if you want the further information, you can go our cell markers webpage, where we have a different cell types. When you can click them, you can see, for instance, here the T cells. So these are the extracellular markers they are expressing, intracellular. For the further information, we usually have some related pages and then related pathways. And all these two resources are really helpful when you are designing your panels. And now when you have your gating strategy and you have your targets, you can start to pair fluors with your antigens. And maybe you have heard about tiers. This is a method that many people are using when they are doing their multicolor panel design. So basically what it means, you divide your cells in three different subgroups. So you have a primary tier, which are usually for highly expressed markers, like for instance, CD8 that is strongly expressed. Then you have a secondary tier, which is usually for markers that are moderately expressed, or you are not sure how strongly they are expressed. That could be also a secondary tier. And then we have tertiary tier, which is for the markers that are low expressed, or they are really rare, or then you just have, for instance, one custom conjugated antibody for that. So then you need to use that one. So those are tertiary tiers. And then usually when you start to do your panel design, you go kind of like upside down. So you start with tertiary tiers because they are, these antigens are more rare. So you usually wanna choose something really bright for something that is low expressed, or if it's really rare. And then secondary tier, it's moderate or to bright expression. So you will choose something that is not too bright, but not too dim either. This is good for lineage markers and also something that change during your experiment. For instance, if you have a disease model, some marker may be really strongly expressed in a healthy sample, but then when you have the disease sample, it's expressed really low. So then you need to have an intermediate brightness antibody, or fluor, so you can detect the both. And then lastly, you have your primary tier, which is then usually the dimmest fluors because it's something that is really highly expressed in the cells. And then just to keep your head straight, what is helpful, you can design this kind of table that you can list the different antigens that you are looking, and then you will organize them based on the tiers. So here's the classification. For instance, CCR7 and CD45RA are tertiary tiers. And then we have CD25, which is secondary, and then the rest of the targets in this table are primary tiers. Then you can list here the cell type, in which cells they are expressed, and then the location. Is it an extracellular, intranuclear, or cytoplasmic? Because this, of course, then reflects how you're gonna perform your experiment. And then finally here, you can list the fluors that then you have chosen then for each of these antigens. And now, lastly, when we have all this done, we're gonna take a look at the instruments. So basically, in a conventional, traditional flow cytometry, you have lasers that are exciting the fluors. And when the laser hits the fluor, the fluorochrome starts to emit protons, and then they will hit to the detector and we will detect the signal. And now different fluors are excited by the different lasers. So for instance, here we have a PE that is excited by the blue laser, and then APC that is excited by the red laser. And then we have filters. So when this PE starts to emit the light, we will collect, here you can see the emission maximum for the PE. We will collect only those photons that will hit to this filter and not anything else. So in this way, we will detect the signal from the PE and APC and they are not overlapping. But then if you see the full spectrum, it's a different story. So here we still have the same PE and APC, but now they are excited by all the lasers that we have in this instrument. So for instance, here we have 5 lasers and we are exciting with each of these lasers, both of these fluors. And then we're gonna collect everything that they emit. So then these photons that we collect, we gonna get this kind of spectral signature. And then if the signature is different enough, we can resolve these different fluors. So for instance, here you see the PE. So there is some blue laser that you have a conventional maximum peak here, but then you also have a lot of signal in yellow green, whereas the APC is on the red laser, but then you can also see a peak here in the yellow green. So there is a little overlapping. So now somebody could ask what's the benefit of this? So for instance, if we have an APC and Alexa Fluor 647, which are both excited by the red laser, and so they are collected for the same detector, and then the emission maximums are overlapping really strongly. So normally in a conventional instrument, you wouldn't use these 2 fluors at the same time in the same panel. If you check their signature in the full spectrum instrument, you can see that the red laser signature here is really similar between these 2 fluors. But then if we go here and see what's going on with the blue laser and violet laser, you see that there is a difference in this signature. And based on these differences here, we can unmix the APC and Alexa Fluor 647, and we can use them together in the same panel. So now this is only one example. There is also a lot of other fluors where the situation is the same. So now it's understandable that by using the full spectrum instrument, we can have way larger panels that we would have with the conventional one. So as mentioned, each of the fluors has a unique spectral signature, and all of these signatures are listed Cytek Fluor selection guide. So you can find it online from this address. And here is just an example of BV421, how it looks like in the instrument. And then a little bit more about the instrument configuration. So here we have a 5 laser Aurora instrument, and everything here that is listed in purple is something that we are providing at BioLegend. Then the ones that are highlighted with blue are our new dyes. So we have KIRAVIA Blue 520, then we have a Spark Blue 550 and Spark Neo 685, and then the Tandems, so BV Fire 640, APC Fire 750, and APC Fire 810. And then we have also few another fluors in our pipeline. So we have BV Fire 810 and PerCP Fire 720. So quite a lot of fluors to choose for your panels. And then we're gonna discuss about different fluor families, so the categories of fluorescent dyes and their respective common features. So firstly, we have a simple organic dyes that are small in size. So they are 0.3 to 2 kilodaltons. And for instance, Alexa Fluors and Bitsy are under this category. And also our new Spark dyes are simple organic dyes. Then we have fluorescent proteins, which are big. They are 35 to 250 kilodaltons. They are really bright normally, like BE and APC, because they contain so much fluorochromes in them. And also they have a lot of tandem dyes available in this category. And our fire dye family, they are protein dyes. And then lastly, we have proprietary dye chemistry. So here, for instance, we have a brilliant violet and it tandems. So this brilliant violet is a polymer dye, and then our new dye KIRAVIA is also in the same category, but it's a different chemistry. So it's a Sony technology and it's a multimer. Okay. So if you are more interested about the fluor families, you can visit our website. So we have dedicated a whole page for this, and there is we have divided the subgroups here, and you can click and see all the dyes fluors we have under each family, and then details about them. So it's really useful as well. So then we take a closer look to our different fluor families or our new fluors. So first I want to start with spark dyes, which are simple organic fluors, and they are primarily designed for a spectral flow, so full spectrum instrument. So the advances of these dyes are that they are really small and they allow high fluorescence to protein ratio, and they are really resilient to fixatives and solvents, and they have a relatively narrow excitation characteristics. And because they are so resilient to fixatives, they are really good for surface staining during the intracellular applications. So you can combine them together with those. And then something you should consider is that they are modest to intermediate brightness. So they are not super bright, but not super dim either. So they are really good for secondary tier antigens, like for instance, cell lineage markers and things like that. So for spark dyes, we have our Spark Blue 550, which is extremely clean. It has an extremely clean excitation and emission properties, and it's resolvable from FITSI and PE. So here you can see the signature, how it looks like in a full spectrum instrument. So the dark blue here is Spark Blue. Then we have PE on green. So you can unmix it because PE has here on yellow green this peak that is different from Spark Blue, and then FITSI that is a little different here in a blue laser and also doesn't have the UV or violet peaks here. And here is just an example how Spark Blue is performing when co-staining with highly overlapping dyes. So you can see here with FITSI or PE or BD570, or you can resolve all the populations really nicely, even here when you have a double positive cells. And then the other spark dye we have is Spark Near 685, which is also has extremely clean excitation and emission properties. And it's resolvable from APC, APC Fire 750, and Alexa Fluor 700. So here you can see how it looks in a full spectrum instrument, and then how it performs when co-staining with highly overlapping dyes. So you can see with all of this listed, there is a really nice resolution between the populations. And then we have our fire dyes, which are protein-based tandems, and they are really good for spectral flow cytometry. So these share the same donor fluor, which is either the APE or APC, which are really bright, and that makes them an excellent tandem dye donors. They have a different signature in a full spectrum instrument because this acceptor molecule is causing a little shift in a spectrum, and also because they are excited by multiple laser, it makes them, all of them has a really unique spectral characteristics. So that allows us to mix multiple different tandems in the same panel. So for here we have, for instance, PE Fire 640, which is really bright and it has a low background, and it's resolvable from other PE tandems like PE Dazzle 594 or PE Sci5. So here you can see how it looks in a spectral instrument, and here how it performs against when you stain with highly overlapping dyes. So you can resolve the populations really nicely. Then the PE Fire 700, it's a similar dye. It's very bright with low background. It's most comparable with PE Sci 5.5, but it has increased stability compared to that. And it's resolvable for PE Sci 5 and PerCP, as you can see here. And here we had a bigger panel having all these targets, but I just show here one. So this is PE Fire 640 against PE Fire 700 co-stain. And it's really nicely resolvable, even the double positive population from the negative population. And here we could ask, okay, so if we have a 5 laser instrument, so it's easier to unmix because you have this full profile between all of these dyes. But what if you have a 3 laser instrument? Can you still unmix these dyes? And the answer is yes. So here we have a staining with CD4 on PE Fire 700, and then here we have CD154 with PE Fire 640, with 3 laser Aurora. So you can still resolve all these populations really nicely. It's not much different what you would see with 5 laser instrument. And here also the PERCP and BE-FIRE 640 without yellow-green laser. So the profile looks really much the same. So you can use with both instruments 3 laser or 5 laser. There is not much difference. And then lastly, we have our APC-FIRE 810, which is an infrared. It has an infrared emission. So it's here like really, really far red. And it's a new fluorophore. And because it's so far red, it can be added to the existing panels pretty easily. And it's resolvable from Zombie-Near and APC-FIRE 700. And it performs really well also with intracellular and intranuclear staining, like you can see here with IFN gamma and then T beta. And as I mentioned, that it's you can add it to existing panels easily. So here I have one example. So this is the old panel that has been used already quite some. So we have already 4 different fluors that are primarily excited by the red laser in the same panel. And then we have BSI7, and then CD4 is on BB510, which is a violet fluor. And here you can see how nicely you can resolve these populations. But what if we would replace the CD4 with APC-FIRE 810? So now our red laser is almost like fully occupied. So we have 5 different fluors on that. And it can be still resolved as nicely as we would have BB510 there on CD4. So this is a really good alternative. The only caveat is that we don't have that many different fluors still for this because it's new, but we are all the time working on getting more of them. And then lastly, we have our KIRAVIA dyes. So it's a novel family, fluor family, and it's now for both conventional and spectral flow cytometry. So KIRAVIA dyes employ a chemically novel backbone that can be loaded with the different fluors. And that, of course, makes it really tunable because you can load whatever you want, basically. And it's smaller than most of the dyes, so 10 to 13 times smaller. And here you can see the profile, how it looks like with the full spectrum instrument. And it's really similar with its spectral signature that Alexa 4488 and FITSI, so those you cannot use together. It's comparable to BB115 and it's very stable. So here you can see FITSI, Alexa 4488, BB515, and then KIRAVIA Blue. So KIRAVIA Blue is here with purple, if you can see, so it's pretty bright. And here how it performs compared to FITSI. So either kept in dark or exposed to light. So it's pretty stable. So there is not much change even though you expose new light. And you can see how much brighter it is compared to FITSI. And then here is the spectral signature between FITSI and KIRAVIA Blue 520. So you see that you shouldn't use them together because they are overlapping. KIRAVIA Blue is basically the brighter alternative for FITSI. And then here, just an example how it performs in extracellular, like cell surface markers. Here is a cytoplasmic staining, and then here is intranuclear staining. So you can use it for all of these applications. And then lastly, something about the factors that are influencing your panel design and performance. So firstly, about the fluor properties, I would like to mention something about tandems first, because we have now a lot of new fluors that are tandems. So you just need to keep in mind that they are usually sharing the same donor molecule, and then what the acceptor is changing. And this, of course, affects the fact that the excitation is the same because the donor molecule is the same. And that's why you can see here that they are exciting in the same laser, basically in conventional instrument. And then, but their emission maximus are different. So this is the way you can separate them. But then when you look at the full spectrum instrument, here I have an example with PE, BE-Sci5, and BE-Sci7. So you can see that BE has these 3 peaks here, whereas then Sci5 has 4 peaks that are like, they have kind of like a shift a little right from PE, and then BE-Sci7 has shift a little more. And now this has changed the signature totally, and that's why you can use them together. But because they still are similar, you need to keep in mind that there might be some spread between them. And then what that means then, so the spreading error refers to an error that is visible after compensation or spectral unmixing has been applied. So basically what it means, if we check like a conventional example here, so we have PE size 7 and APC size 7 together. And here you can see the uncompensated situation where the APC size 7 is actually spilling into PE size 7. And now to get rid of this spill, we can compensate. So we compensate so that the APC is now nicely here, APC size 7 and PE size 7 here. But this here is like an ideal situation. In a real life, when you need to compensate a lot, you maybe see this kind of fuzzy cloud of cells. So this means that now you have a spillover spreading error here. And the more basically you need to compensate, the larger is your compensation, the more you have error, most likely. So there is basically 3 rules that you need to keep in mind when it comes to this spreading error. So firstly, there's more spreading error occurs with more fluorophores is in the detector. So what that means, so here is an example that you have single stain cells with BV785, and you can see nice resolvable population here. But then you add 13 more fluors in the same tube and you stain them, you start to see spread or spilling here, and it's not anymore that easy to detect this single positive BV785 population. So now, because all these 13 colors that we added to this panel, they basically reduce the staining index of BV785. The other thing is that the more spreading error occurs, the more fluorophore spills into another detector. So basically what it means, so here we have this kind of trumpet effect. So when you go to the really high end of this 4A, you can see that it's actually spreads. And then the problem comes here when you add the 4B in your same staining. So this double positive population here is kind of difficult to resolve because the 4A is spilling to 4B. Okay, so this is not end of the world. We can handle this situation in a few ways. Either you change some dimmer fluor for this 4A so that it's not spreading that much, or you titrate your antibodies. So you use lower concentration of this 4A so that you can get a cleaner plot with it. Or the last option that you can do, you can choose some brighter fluor for this 4B so that it shifts a little more right and it goes away from this population that is spreading. So this takes us to the third rule. So the more spreading error occurs with brighter fluorophores intensity. So if you have something that is really strongly expressed, like CD8, you shouldn't design really bright fluor on that you won't see this kind of spread. And now one could ask, like, why this is so important with full spectrum instrument, because of course this happens also with conventional. It's because of the first rule, basically. The more spreading error occurs with more fluorophores in the detector. So full spectrum, we easily have large panels and everything is detected and not divided with different filters. So that's why now you need to be really careful when you design your panels to avoid this spreading. This is just another way to illustrate this. So we have antigen Y stained with fluor C and antigen X stained with fluor A. This is a nice situation. So there is no spilling or spreading. So, and because of everybody is nicely at their own places, there is no reduction in the staining index. So you can resolve these 2 fluors. But if we replace the fluor A with fluor B, which is then spreading to fluor C, that actually reduces the staining index of fluor C. And now we can see that there is spreading error. And it's kind of like a spread, this peak here. And now if we think the situation that we would dump in 5 other fluors that all will spread, it might cause the situation that staining index goes so low that we cannot anymore unmix these 2 fluors. So that's why we need to titrate the antibodies and be smart when we design our panels. The other thing that could help you to design your panel is this matrix, a spreading matrix. So it's available for 3 laser and 5 laser instruments. So how you read this matrix, basically, if you see red, you know that, okay, possible this combination is causing spreading and also reduction in the staining index. So if you have PE together with BV57, you can see the red box here. So it means that PE is actually spilling to BV57. And you should avoid, if possible, this combination. So you are not, because this will reduce the staining index of BV570. Of course, in some situations, if you design PE on something that is really low expressed, lower than CD4, and then you will design BV570 on something that is really strongly expressed, maybe they can compensate this reduction in the staining index, but you are on the safe side if you try to avoid these red boxes. So that will help you. Then if you want to see how this looks like in a real situation, so why this box is red, so here you can see the same example, so PE with BV570. And here you can see the full spectrum signature for these 2 different fluors. And here is the primary laser that is exciting BV570. But yeah, so you can see the signature here, which is really similar with PE. So this means that PE is probably affecting on BV570 and causing reduction in the staining index. And actually this reduction is all 83%. Whereas if you have opposite situation with PV together with APC, so APC is excited primarily with the red laser. So here you can see the signature of APC and PE, which are totally different. So the PE is causing like 0 reduction staining index to APC. So this couple here is good, and this is something you maybe should avoid. So lastly, I would like to pull this together by showing some helpful web tools and then some closing thoughts about panel design. So if you are not sure which fluors are bright and which are not, this is a really good table to use. So it's for 5 laser Aurora that contains 65 dyes, and the higher is the column, the brighter is the dye. So for instance, here PE, that is normally the brightest, and then it goes all the way down, something that's really dim, like PerCP here. So this is something you maybe wanna check. And then, of course, we have at BioLegend our Aurora Spectral Analyzer. So most of those graphs that I show today are from that tool. Then we have our panel selector that will help you with your panel design. So basically you can go to the website, it gives you this kind of selection. So you just select the lasers you have, which species you have, and then you select your targets, which after you will get this kind of table, and you can start to choose for different targets the different fluorochromes that we have available. And this is actually nice because once you have clicked one, you cannot click it anymore. So you are not gonna do that many mistakes. And also it gives you the brightness index of different fluors. And of course, also it shows what we have available. So you are not gonna plan CD25 on BV750 because we don't have it. And then last but not least, we have Cytek Spectrum Viewer. So this is also a really handy tool. So basically this Cytek Spectrum Viewer gives you the similarity matrix. So you have here numbers from 1 to 0. And 1 means that the dyes are, they are like matching perfectly. So the spectra are identical. Of course, if the dye is the same, that happens, like BV510 is the same dye. And then something that is kind of similar, like APC Fire 810, and then what we have here, APC Fire 750. You can still use this together, it's not that bad, but anyways, they are closer to each other than, for instance, PV421 and PE. So if you have number 0, they are completely different. And how you can then use this matrix, so when you go to the website, you can click here, double click the dyes, then you have already your panel. So you just double click here what you have chosen, for instance, KIRAVIA Blue 520 and Sparkneer 685. It will show you how it looks, the spectral signature of each dye. And once you are ready, you can click this similarity and complexity. And then it will give you the overall complexity of your panel. So for instance, in this case, we had 9 dyes and it gave the complexity index 2.15, which is pretty good. So for instance, this kind of small panel with 9 dyes, the complexity index, if it's something between 2 to 3, it's okay. If you have a huge panel like 35 colors or so, your complexity index can be something like 46.4, and it's still okay. So it ranges between 40 to 50 when you have like a really large panel. So this is just like a good thing to check before you really start to work with the panel, so how complex it actually is. And then just a few tough combinations that maybe you just want to remember by heart because they are just not getting along. So we have BE and BV570, PSci5 and APC, BB515, Alexa 4488, and then BV421 and SP436. So the spectral signature is really similar between these pairs, and that's why you should avoid those. And then just to review this all, so let your biology influence the applications of Flow. So when you know what you are looking at and what you want to see, it helps you to design your panel. And then always start with the theoretical panel and remember the controls. I didn't talk much about them today, but you need to have all the controls that you would have with conventional instruments, single stain and non-stain controls. And this helps you to assess the spread. And then after you have check your panel, you don't be afraid to redesign if needed. Try to avoid challenging combinations and try to maximize the resolution. And then you always need to perform the stain, and it's recommended, especially if you have valuable samples. So try to do some kind of test run first with something that is not that valuable, so you can be sure that your panel is working. And then don't be afraid to do few smaller subpanels if it becomes really complex, your big panel, so it can help. And then there is spread. When you have a large panels, there is always spread, but we just need to manage it. And that it's how you can do that. So you titrate your fluors and try to choose something that are not spreading that badly. And then of course you can work with BioLegend. We are always happy to help with the panel design. And I would like to thank you for your attention. And if you have any questions or comments, I think we have time for those as well. So thank you.
Ville, you're muted.
Sorry, yes, thank you, Sanna. So there has been a few questions in the chat about the availability of these dyes, or when are they commercially available? And also you were speaking about 3 different dye categories, the chemistries. Are some of these dyes, or when people are thinking at which dyes they might want to use, should they think more about the color of the dye or the chemistry of the dye? Like are different dye groups overlapping in their spectral properties, but so one is better for extracellular staining versus intracellular staining, or are each group spectrally different?
So necessarily no, like if we have 3 different categories of fluors, they still can have, like, they can be excited by the same laser, just a different chemistry. So I think if you are designing your panel, the thing that is most important is the color, like how it's excited and emitted, not that much the chemistry, if that was the question. The chemistry is important when you think you need to fix your samples, and if you have, for instance, protein-based dyes, so they necessarily are not the best choice because they can precipitate. So that's the thing when you need to consider about the chemistry. And yeah, we have commercial available. we have APC Fire 810 commercially available, yes. I don't remember now by heart how many conjugate we have, but you can find it from our website. And if you want to know something specific, you can always email me and I can check with the production what we are having in the pipeline.
And how about are all these dyes visible in different Spectra viewers or only on BioLegend site? Like, for example, Fluorofinder, are these included in their database?
Some of them, at least. Yeah, they all are actually. Yeah, thanks, Lisa. They are now. I wasn't sure about that. Yes, that's a good question. They are there. Mm-hmm. Yeah, so they are on Cytek, and most likely they are also on Fluorofinder. At least most of them are, I know, but I haven't checked all of them.
Okay, thank you. It looks like there is no more questions. If any attendants want to ask anything, please write in the chat or unmute yourself. But if there is no more questions, I want to thank Sanna once more.
Yeah, thank you all. That's my pleasure.
Thank you so much.
Thanks everyone for coming.